Hello, everyone. Good evening. I appreciate the time of everyone joining us here at the Mandalay Bay and everyone that are watching online. Welcome. This is CMP210, Modern Applications and Infrastructure Perspective. If you are in this session, you are a DevOps or an architect. You are running applications on EC2, and those applications are either modern in their nature, and you're looking for ways to optimize them, or you are designing a new workload, and you need to decide what compute options will work best for you. My name is Yael. I'm a solution architect, and I focus on compute services on AWS. I'm in the tech industry for over 10 years, and this subject is close to my heart because I've been in and around DevOps teams for this entire time. At AWS, I work with customers from all sizes, and I help them solve their challenges around operating compute services on AWS. And one of the customers I work with is Mobileye, and Jeremy is representing Mobileye here.
Hello, everyone. My name is Jeremy Atlan. I am an AI application architect at Mobileye, and I am really excited to be here today to tell you a little bit about Mobileye and how we develop and run modern AI applications.
So thank you so much, Jeremy. Mobileye is one of the customers that are making very optimal use of compute services at AWS. Their super high scale brings them to implement advanced and sophisticated architectural patterns, so I'm sure that everyone will have a lot to learn from it. So thanks for joining, and let's get started. So let's start for a second why we created this session. There is a strong motion in the industry to move to develop modern applications, move to use technologies like containers and serverless and event-driven architectures. And there are a lot of good reasons to do that. No matter what's the reason that brought your organization to migrate to modern architectures, when you get there, you can implement optimization very easily and effectively. And what we want to show in this session is how you can gain optimization by designing modern applications. Modernization and optimization are very good friends, and this is what we're going to talk about in this session. So this is the outline of the agenda. We will start from talking about modern applications and their requirements from the infrastructure, the different EC2 instance options and provisioning and scaling tools that you can use for modern applications. And then we'll go through the most common practices to design a well-architected compute platform on AWS. Jeremy will then present how these practices are applied at Mobileye with their super high-scale data platform. So you're running applications on AWS. You want them to be resilient to failures, and that if they do fail, they are able to recover quickly and automatically so that you don't need to be on call 24/7. You want to provide developers an agile experience so that they can deploy small pieces of their code easily and quickly. And you want your workloads to be elastic and efficient because, especially lately, your leadership doesn't stop talking about cost optimization. The way to achieve all of these goals is through modern application development. And what I mean by that is the application is usually built from small, loosely coupled, modular, independent components. Each component is a minimal function microservice. Different microservices communicate over APIs, and together they achieve a broader use case. So this allows fast deployment and innovation. It also allows to adapt to modern compute, optimal compute, that minimizes waste of resources and reduces cost. So with modern applications, a lot of the business logic has been offloaded to the infrastructure. So it becomes even more critical than what it was in the past with legacy systems to invest in the infrastructure. And in order to truly take advantage of the benefits and capabilities of modern application architecture, you should implement similar practices to the compute. Make your compute flexible, dynamic, and modular, same as you're doing for the application layer. So let's get to the actual content. You have a modern application. Choosing the right model to package, run, and deploy your application on AWS depends on a combination of your business objectives, the amount of granular control you need from the infrastructure, and the amount of effort you're willing to invest in order to maintain those applications. Most of our customers choose one of the options on this slide. Amazon EC2, the traditional way to run compute when you want direct access to the underlying resources. The application can still be modern in its nature, microservices that run on EC2 instances. But at some point, managing a lot of microservices on plain EC2 can become complex and inefficient. And then some would choose containers or serverless. Containers help streamline the application management across different environments, and it also helps orchestrate a high number of applications much more efficiently. You still have access to the underlying infrastructure, but you need to maintain it in a different way than what it was before. So that requires you to have new skills and specialty in the technology that you choose to work with. If you don't need access to the underlying infrastructure at all, you can choose to work with a serverless solution, for example, AWS Lambda, that lets you deploy code without having to think about the infrastructure. Now, although containers and serverless are similar, they do have some differences in their approach. Containers allow you to have access to the underlying infrastructure, and you pay based on consumption, while serverless abstract away the infrastructure, and you pay based on a request rate. Choosing the right model depends on a combination of the objectives that I mentioned earlier. We're not going to focus on that selection. Today, we're going to focus on the cases that do require some level of control of the infrastructure, and we'll talk about the services and tools that we have today in order to help you do that in an easy way. So let's start by reviewing the compute options that you have while using Amazon EC2 and how you can best consume those resources. So you have an application to deploy on AWS. You already know what is its properties, how many resources it needs. AWS offers today more than 500 instance types built with different resource specifications, and they offer different performance, size, and price. You have the broadest and deepest compute platform with a wide range of processors to choose from. But how do customers make that selection and decide where to start and what instance works for them? So my recommendation is work backwards from your workload performance requirements. And have in mind, there is a good chance that multiple instance types can power your application workload. Different instances that have different performance requirements. And the more flexible you are on the instances you are willing to work with, the better you have the chances to get the best compute offering for your workload. So the process of selecting instances starts from answering these 3 questions. Number 1 is what processor can your workload use? That means you need to understand what is the software stack of your application and whether you can take advantage of ARM processors. Number 2, what are your workload's performance requirements? What is the amount of minimal CPU and memory that you need, or anything else, accelerated computing, for example? And number 3, what is your workload consumption pattern? Can you use burstable performance instances? Can you use interruptible instances? After you answer these questions, you'll get a list of instance types that you will be able to test and qualify and make sure the application actually behaves the way that you expected it to. Now let's see how this translates into the EC2 platform. Understanding the resources and performance provided by different instance types at the EC2 platform will help you select the right instance that works for you. Each instance combines resources of CPU, memory, storage, and network. The instance naming convention helps you figure out what properties you're getting from each instance. So let's take, for example, M6G extra large. M is the general purpose instance family. An instance family is a collection of instance types that are designed to meet a common goal. When new technologies are introduced into EC2, new generations will be added to expose those technologies. And what we see here is the generation 6. Then G represents Graviton processor, and extra large represents the amount of resources that you get from this instance. Each instance family has a CPU to memory ratio, but each instance size provides twice the number of resources comparing to the previous size. So let's take an example and understand what it means to be flexible on the resources that you're willing to work with. Let's say, for example, that you need 32 gigs of RAM for your application. The obvious choice would be to go for an R6i, the memory-optimized instance family, in the size of Excel. But I can get the same 32 gigs of RAM from a general memory instance from M6i to Excel. So if you play around with the different instance families and different instance sizes, you'll see that you can choose different instances to get the resources that you need. And being flexible will help you get the best compute offering for what you need. The next choice is around the processor. And today you have Intel, AMD, Graviton processors, and Mac. Intel has the longest collaboration with AWS, and you have more than 300 instance types to choose from based on Intel processors. AMD is showing a strong adoption due to the lower cost of their instances comparing to Intel-based instances. Mac instances help you run Apple applications in the cloud. And of course, we also have the Graviton instances. Graviton instances provide the best cost-performance ratio comparing to other processors in the cloud. And you can get up to 40% price-performance improvement comparing to other instances. Now, when you approach your application modernization journey, I encourage you to consider the Graviton processor for the best price-performance ratio. And some people think it's much harder to use Graviton for your applications. If you're using a Linux OS and you're using open source frameworks, you probably can benefit from using Graviton without investing a lot of effort in order to do that. Now that you have an understanding what processor you can use and what are the performance requirements of your application, you need to approach the purchase option selection. And you can use spot instances, saving plans, and on-demand. Spot instances are the spare unused capacity of AWS, and you can get the best pricing point for the capacity that you need, with the caveat of having those instances interrupted if AWS needs that capacity back. Saving plans are another way to gain discount of up to 72% discount in exchange to 1-year or 3-year commitment. And if you have spiky workloads, stateful spiky workloads that don't fit very well to Spot or to saving plans, you can go for on-demand. Let's talk a little bit more about Spot, because Spot is a perfect fit for modern applications and containers specifically. A Spot instance can be reclaimed by AWS if it needs the capacity back for on-demand. So for your application, it means two things. One, your application needs to be tolerant to that instance replacement. And two, your application needs to be able to be flexible on the compute options so that if you're using one instance type, you can move to another one. Modern applications are stateless and elastic. Replicas will be created and destroyed frequently based on changing demand. So that would be very similar to what happens when there is a spot interruption. And they are lightweight, so typically they start just in a few seconds, and they can work with the spot interruption event handling. And since you can bin pack different microservices to run on shared instances, they're also very flexible on the instance selection. So that means that without investing a lot of effort, you can implement Spot for your modern applications, as long as you have a way to choose the compute that would work for you. And that's exactly what we're moving on to talk about. So I'm going to recap quickly what I talked about until now. The compute services on EC2 can be packed into 3 layers: compute options, purchase options, processors, and different instance families. The way to consume them are using launch services. And launch services communicate with some scaling behavior that impacts the amount of resources that you consume throughout the day. So now we're going to move on to talk about launch services and scaling behaviors. We'll start from talking about auto-scaling groups that are the best practice when you decide to package your application as an EC2 AMI and deploy it into EC2 instances. And then we'll move on to talk about EKS managed node groups and Karpenter. So auto-scaling groups are a fully managed service that contains a collection of Amazon EC2 instances that are treated as a logical grouping for the purpose of automating management and scaling. Sometimes some people forget that auto-scaling groups also have a lot of capabilities that will help you manage the lifecycle of the instances. And you can manage things like automations, bootstraps, scripts, shutdown scripts, integrations. For example, the integration with managed node groups is very popular. You can also combine different compute options. So in a single group, you can have Spot and on-demand. You can have different instance families and different instance sizes, and even Graviton together with x86 processor instances. Like the name implies, auto-scaling groups also allow dynamic and automated capacity changes using scaling policies. So when using scaling policies, there is a spectrum between automatically scaling when there is a need for resources using simple and target scaling, and pre-scaling resources to accommodate for future needs using scheduled scaling or predictive scaling. So there is a trade-off between proactively and reactively scaling. The trade-off is between performance and cost. Scheduled and predictive scaling will be useful when there is a predictable traffic pattern, some historical pattern that can impact what is going to happen in the future. On the other hand, if your application is lightweight, small, it starts fast, it will be much more efficient to use reactive scaling, and it will also be more dynamic and allow you to react to real-time conditions. Now, when you package your application as an EC2 AMI, the best practice would be to work with auto-scaling groups that will give you the most capabilities to manage the lifecycle of the instances. Today, a lot of customers choose to run their microservices on Kubernetes with Amazon EKS. And this is what we're going to talk about now and dive deep into provisioning and scaling tools for Amazon EKS. So Amazon EKS is a managed service that lets you run Kubernetes on AWS without needing to install, operate, and maintain your own Kubernetes control plane. Without diving too deep into the Kubernetes architecture, the Kubernetes cluster is built from control plane nodes that run the Kubernetes software, things like etcd and the Kubernetes API. And these nodes run in an AWS designated account, and customers don't have access to those nodes. The next type of nodes are worker nodes that make up the data plane, and they run the actual container images that support your applications. In order to build a resilient, highly available, and elastic data plane, you need to deploy your worker nodes across multiple availability zones, take advantage of cost-effective compute, and have the capability to scale your resources automatically. Now let's focus on ways you can provision worker nodes. You have 3 options: Fargate, the most managed option; managed node groups that handle provisioning and updates of the data plane, but you do have access to the nodes, and self-managed nodes that are the least managed option, and you have full responsibility for configuring and maintaining those nodes. I'm going to dive deep into each one of these options now and talk a bit more about it. So managed node groups automate the provisioning and lifecycle management of EC2 nodes, and you can create, scale, and upgrade managed node groups directly from the EKS console or API. There is a direct integration between managed node groups and autoscaling groups that we talked about now. So when you provision a managed node groups, it runs as part of an EKS managed autoscaling group. So that lets you take advantage of all the capabilities that autoscaling groups exposes, like running across different availability zones, combining different instance families, and so on. So a lot of the operational overhead is offloaded to the autoscaling group, but you do have access to the resources. Now, when working with EKS node groups, a common practice is to scale nodes using the cluster autoscaler. The cluster autoscaler is a popular open source solution responsible for ensuring that your cluster has enough nodes to schedule your pods without wasting resources. Unlike autoscaling group scaling policies, the cluster autoscaler runs as a deployment inside your cluster, and it's aware of scheduling decisions and pod events. So one of its goals is to bridge between the Kubernetes abstraction into the autoscaling group abstraction, where the nodes actually run. Now, let's understand how cluster autoscaler works by looking at a scaling activity in the flow in this slide. This activity starts by HPA, horizontal pod autoscaler, that creates a new pod in response to metrics. That pod is created, and if there aren't enough resources to run, it becomes pending due to insufficient capacity. Then cluster autoscaler is in charge of identifying that event and provisioning a new node for that pod. How it works is it looks on the list of autoscaling groups that it's in charge of, and it looks on the size of the pod. And for each autoscaling group, it simulates the amount of resources that it will get. But it assumes that the amount of resources that each autoscaling group will provide would be the same. So that means you need to architect your autoscaling groups in a way that each autoscaling group has instances with the same size and the same labels and taints. You can't combine spot with on-demand, and you can't combine instances from different sizes. So you remove a lot of the benefits that we had in autoscaling groups. And that adds a lot of complexity, because if you want to have the flexibility to use all the compute options that you have on EC2, you need to maintain a lot of autoscaling groups. Now, while cluster autoscaler is an essential piece that bridges between Kubernetes into autoscaling, it also brings a lot of challenges and reduces the flexibility that we want to have when working with modern applications in the cloud. And it works fine for some applications, but when you want to run sophisticated applications on Kubernetes, a variety of different workloads that have different needs, and you want to combine Spot with on-demand and run on multiple availability zones and use different instance families so that you can get to very high scale with Spot instances, like we will see in Jeremy's presentation in Mobileye, it becomes very challenging. So that's exactly the reason that Karpenter was created. And that's what takes me to talk about Karpenter now. Karpenter was designed to overcome the challenge of managing a lot of autoscaling groups in order to be able to use the flexibility of the compute services in AWS. Karpenter provisions EC2 capacity directly based on application requirements without the middleware of node groups. It's an open source scaling solution that is in charge of provisioning new nodes in response to unschedulable pod events. So let's see now how it works for Karpenter and how it's different from cluster Autoscaler. We see now a similar flow of a scale-up activity. HPA created a pod. That pod became pending because there aren't enough resources in the cluster. Now Karpenter is in charge of provisioning a new node that can run the pending pod. On the right side of this slide, we see what we have available for Karpenter to provision. Karpenter, in this case, can provision resources, EC2 instances, from 2 availability zones. It can do that for multiple instance families. In this example, we have C5, M5, G instances, Graviton instances, and by default, Karpenter simply uses all available options on EC2 unless you decided to exclude something. When it provisions a new node, it simply creates an EC2 API request with a list of instances based on the size of the pending pod, and it can combine spot and on-demand. So for example, in this case, the pod has a node selector of capacity type spot. So Karpenter will simply provision a spot instance for this pending pod. So we can see that Karpenter takes advantage of all the flexible compute that we have on the cloud without having a lot of overhead for you. So you get a solution that, on one hand, abstracts away the infrastructure from you, but you do have access to the nodes. They run in your account, and you have the flexibility and control to do whatever you need with these nodes. The last compute option to run worker nodes on EC2 is AWS Fargate. Fargate is useful if you don't require any access to the underlying instances. There are some limitations, and I encourage you to look into that separately. One of the patterns that we see our customers is utilizing is running some applications that have static behavior on Fargate on demand, and run the rest of their applications on a flexible fleet of spot instances combined with on-demand, provisioned by Karpenter. So after we went through all the different compute options and provisioning tools, I want to go now over a few practices that we recommend every customer to use when they create their compute environments on AWS. The first one is compute flexibility. And like I said, taking advantage of all the capacity types that you have on EC2. Building an architecture that is able to apply compute flexibility will help you reach better resource performance, use lower price of compute offerings, and you'll have better availability of capacity. You'll avoid situations where there is no capacity for what you're looking for. And we'll see in Jeremy's presentation how they use a super high scale with very popular instances, with spot instances, because they're able to be very flexible. The easiest way to implement this flexibility is using an attribute-based approach. Attribute-based approach means that you build your requirements based on performance requirements, like amount of CPU or memory, and not based on instance types. So on one hand, you get the flexibility and use all instance types that are available for you based on your requirements. But on the other hand, you don't need to be familiar with all the instance types that are available today, more than 500 instance types, and it reduces the overhead for you. Deploying across availability zones is another way to implement flexibility. And there are 2 reasons to do that. One is gaining high availability and fault tolerance in case of a major failure occurs in an availability zone. And the second one is getting access to more capacity if your application needs a lot of compute. A common practice that customers implement is use Kubernetes native scheduling constraints, such as topology spread, to make sure that replicas are spread between different availability zones. And then you need your provisioning tools to respect that spread and provision instances across different availability zones. Instance lifecycle management speaks about the ability to proactively and reactively replace your instances in response to hardware failures, manage spot lifecycle, be able to gradually recycle all the instances in order to deploy a new version of your application. This is another thing that you need to make sure that is provided in the provisioning tools that you're working with. And that takes me to summarize this section of this presentation by talking about the different provisioning tools that we went through and the scaling approaches. Auto-scaling groups are the best practice when you decided to package your applications as EC2 AMIs and deploy them to EC2 instances. If you decided to go for containers with Kubernetes, managed node groups and auto-scaling groups will provide high value with minimal operational overhead if your workloads tend to be more static and consistent. When you have large clusters with workloads that encounter periods of high spiky demand, or if you have diverse compute requirements, Karpenter should be your best choice. On one hand, it abstracts away the infrastructure from you and lets you be flexible very easily. But on the other hand, you do have access to the resources. And the last option is Fargate when you don't need access to the resources and you want to give Fargate to manage and provision resources for you. You can combine these approaches together. So for different applications that have different requirements, use a different approach. Now I invite Jeremy to show us how in Mobileye, with their complex data platform, they choose different services for different use cases.
Thank you, Yael. Over the next few minutes, I would like to tell you a bit about the technology we develop at Mobileye, some of the many data applications behind this development, and the way in which we utilize AWS cloud services to run this in an affordable and scalable manner. You will see how we chose different solutions for different applications, depending on attributes such as modularity, fault tolerant, or a degree of modernization. In case you haven't yet heard about us, at Mobileye we are in the business of making roads safer and saving life. We are a global leader in developing technologies for driver assistance solutions and autonomous vehicles. And as of today, there are over 100 million vehicles around the world containing Mobileye technologies in them. Underlying our technologies are a multitude of sophisticated, artificially intelligent algorithms responsible for all hosts of detection, prediction, and decision tasks, including identifying and categorizing road artifacts such as signs, lane markings, and debris, predicting the motion of vehicles and pedestrians, and deciding on safe driving maneuver. Fundamental to the development of this AI algorithm is data, and a lot of it. At Mobileye, we have massive amount of data in the form of RGB images, depth maps from LiDAR and sonar scanner, mapping data, and more. This data is used by many different teams at Mobileye for many different types of purposes. One example of database AI application required in my team are ground truth creation applications. Applications that using machine learning and computer vision algorithms to automatically create ground truth data. This process, sometimes referred to as auto-labeling, takes raw sensor data as input and output labeled data for machine learning. Another example of data application on our team are our deep learning training application. This takes in the auto-labeled ground truth data and output a machine learning model. Other examples include applications that process, transform, aggregate, and search over different types of data. Common to all of the applications is the reliance on end use of data. However, they differ in many other properties such as time duration, dependencies, scale, resource requirements, etc. Some applications are lightweight and modular, while others are large and monolithic. So on the one hand, we have a long list of required heterogeneous applications. On the other hand, AWS supports a wide variety of services and tools that seemingly address every type of application workload you can imagine. The challenge, how do we find the optimal match between them? What is the right type of compute and the right mode of application management for each one? How do we architect the ideal solution for each individual application? As Yael mentioned earlier on, one size does not fit all. Some of the guiding principles behind our search for optimal solution architecture are the need for scalability, reliability, security, performance, and perhaps most importantly, cost optimization. In the next few slides, I will walk you through some of our data application use cases and the solution architecture we have chosen for them. You will see how the properties of the workload, including their modularity, size, and tolerance of failure, impacted the solutions that we chose. Let's start with the heart of our development pipeline, the machine learning model training. Training sophisticated machine learning models, such as vehicle detection model, requires a very specific and specialized hardware and software infrastructure. Contrary to other data applications that will span thousands of jobs on individual instances, a training project will typically include no more than tens of experiments, each of which will run on up to several dozen GPU instances. Given the relatively high cost of GPUs and the fact that training often runs for a day at a time, our workloads are usually optimized for specific instance type in order to reduce the cost. Given all of these properties, we have found AWS Managed Training Service, Amazon SageMaker, to be an ideal framework for training. Amazon SageMaker allows us to program each of our training jobs to run on a fixed number of fully configured GPU instances of your choice, and will manage the full training flow. Let's move on to another use case. Our next example is data processing application that takes some form of data as input and use it to generate new or refine data as output. An example of simple data processing application is the script that runs on an input video file and outputs the individual frames of the video. We typically run such processes on hundreds of thousands of videos in parallel. This application is not dependent on specific hardware infrastructure and can run on a wide variety of instance types. The script runs for a relatively short period of time and is extremely amenable to spot usage, since if any specific job fails, we can simply rerun it until it passes. This kind of job is ideal for AWS batch. In AWS batch, we can define the desired script, the required underlying container, and the resource needs and rely on the managed service to orchestrate the spawning and execution of all of the job. Using AWS batch, we have reached parallelization on the order of hundreds of thousands of jobs. However, AWS batch treats each job as a single entity, and this doesn't allow us to run more complex workloads. For more sophisticated data application, we chose Amazon EKS. Which brings us to our next category, data application running on Amazon Managed Kubernetes Service, EKS. Here is where the real fun begins. Many of our applications are far more complex than the simple video to frame conversion example we just discussed, requiring a more sophisticated, interdependent flow, a breakdown into many smaller components or microservices, and a high level of autoscalability. These needs are addressed by the Kubernetes architecture. The next three examples will demonstrate a few ways in which we use EKS. One type of data application that relies heavily on the Kubernetes architecture is our data search service. Oftentimes, data engineers will require a subset of data samples that match a certain query, either to evaluate our algorithms under specific setting, or to enhance the algorithm to better support those settings. For example, if our vehicle detection algorithm is failing at identifying pink cars due to their underrepresentation in our training dataset, we may want to collect all of the data sample with pink cars in order to increase their representation. We developed this kind of real-time interactive application for developer use on top of Kubernetes. We support this using Kubernetes component, manage the number of resources based on demand using horizontal pod autoscaler, and use Karpenter for instance selection. We deploy our cluster across availability zone in order to increase resiliency and use spot instance in order to reduce cost. Let's move on to the next use case. Here is another example of an application that we deploy to EKS, but with an added level of sophistication. An additional degree of complexity is introduced by data analytics application that are based on MapReduce functions. For this, we rely on the dedicated Spark support for Kubernetes. For example, we sometimes require a detailed analysis of the performance of our vehicle detection algorithms across subsections of different properties, such as vehicle type, weather condition, traffic condition, and more. Sometimes conducting these queries requires collecting massive amounts of data from multiple sources and merging them together into a single coherent table. This in turn requires us to scale up our compute capacity very quickly and for a relatively short period of time. These are by no means simple challenges. This requires a solution architecture comprising of multi-component and multi-player, resulting in Spark-based solution running on EKS. At the compute level, we use AWS Karpenter to manage elastic and automated instance allocation. We program Karpenter to find stop instance across multiple availability zones to increase availability while reducing cost, and rely on its auto-scaling feature to automatically launch the required instances when a Spark job is submitted and scale them down when the job finishes so as to minimize the idle resources. To address the challenge of the amount of input data, we use Spark to load our file in a distributed manner using well-known hashing and data shuffling algorithms. This is followed by Spark MapReduce algorithms. Thus, we find that our solution is comprised of multiple components and multiple layers of the solution architecture, including instance allocation by AWS Karpenter, storage management by Kubernetes PVC, and MapReduce function using Spark. Moving on to our fifth and final use case, DAG application on EKS. Many of our data applications include complex flows with multiple stages and with strong dependencies between them. These are commonly referred to as directed acyclic graph or DAG workflow. There are several frameworks that extend Kubernetes to support DAG workflow. Our frameworks of choice is Argo. Using Argo, we are able to define a dependency diagram, monitor the flow as it progresses, capture checkpoints along the graph, rerun specific components, and so on. Following the design principle of modern application, workflows are broken into small steps, each of which are modular and fault-tolerant. In our workflows, most of the container applications run for up to 10 minutes and require up to 10,000 parallel CPU or GPU instances. The resources for the container are aggregated by Karpenter, which takes care of choosing the best combination of instance type while maximizing our use of low-cost spot instances. When steps along the workflow are completed, Karpenter terminates the inactivate instance so that we don't pay for the instances that are not needed. On this slide, we see a typical DAG workflow. Each node represents an individual container application, and each edge represents an application dependency. Each job on the graph can be associated with a different specification of resource requirement. Some with GPU, some without, some with more required memory, and some with less. The ability to define the requirement as this resolution enables better resource management and leads to lower cost. The combination of a dependency graph-based workflow together with nested parallelism at each stage results in faster runtime. Argo workflow supports the option of checkpointing result at any junction, thus facilitating easy recovery in case of failure, saving the time overhead and cost of having to rerun the entire flow. Furthermore, in the case of code modification or data changes, we can again rerun some portion of the graph rather than the entire flow. Here, we see a graph from Grafana, an open source library for visualizing resource metrics. When developing highly scalable EKS-based applications, especially ones that utilize tens of thousands of underlying pods, it is important to have tools in place for measuring and analyzing pod startup and usage pattern throughout the course of the application lifecycle. Here we show the instance creation during one step of the Argo workflow, in which 6,000 pods were needed. It took under 10 minutes for us to acquire 1,200 worker nodes with 6,000 pods. On all of the 1,200 worker nodes were low-cost pod instances. Our use of EKS for our data application and services is summarized in this simplified three-layer diagram. All of the Kubernetes-based applications are run on the same cluster. At the lowest level are compute resources, including specialized instance type, and the potential for cost saving using spot instances. These are managed by orchestration tools, including Amazon EKS and Karpenter. At the top level are rich frameworks that build upon the EKS infrastructure, enabling a wide variety of complex data solutions. One of the advantages to this architecture is the separation between the domain of the EKS application owned by one team that specializes in DevOps and infrastructure, and the domain of the data engineer. Another advantage is that the same EKS cluster can be used for different data frameworks, with division between projects managed via namespacing. In conclusion, I have given you a small taste of the data application development done on my team at Mobileye. I have described how different applications are solved using different solution architecture. One size does not fit all. On the one hand, we have applications such as machine learning model training that require high level of hardware and software specification. These are solved using the highly specialized Amazon SageMaker managed training service. On the other end of the spectrum, we have a wide variety of applications that are provided using the highly flexible and highly extensible Amazon EKS service. These applications are built from loosely coupled, modular, and fault-tolerant containers. Implementing this kind of modern development practices enable us to make use of more sophisticated and efficient computer offering. In between, we have relatively simple applications requiring high scalability but relatively low flexibility. We summarize our approach to architecting our data application to support the criteria we set forth of scalability, reliability, performance, and cost optimization. The solution I have described here for our data application are by no means the only one. You might think that other solution architecture and other AWS services better fit your need. Thank you for your attention.
Thank you so much, Jeremy, for sharing that. So other than the super interesting business case that Mobileye has, Jeremy showed how when they had sophisticated modern applications, they decided to run them with Spark and Argo CD on top of Kubernetes and take advantage of Spot and flexible compute and Karpenter to gain the most powerful compute for their workloads. So I want to quickly summarize a few key points that you can take from here. Just like Jeremy presented, one size does not fit all. So you can build your infrastructure architecture to support compute flexibility because that will allow you to take advantage of optimal compute when you need that. When you approach your selection process of instance types, go through the process that I described in the beginning of the session. What processor can you use, what performance requirements your applications have, and what is the runtime pattern of your applications. Then use attribute-based selection in order to build the list of instance types that you can work with and integrate that with the provisioning tool that you work with. Lastly, apply automation and take advantage of the EC2 tools to perform some of the management for you so you don't have a lot of overhead and you can be sure that you're using the best practices provided by AWS. So thank you so much for staying with us until now. Please, before you move on to the rest of your evening, take a minute just to rate us on the AWS app so we know how useful this session was for you. And have a great evening.